See, welcome back. Today we are going to discuss about the MMF method of finding voltage regulation of an alternator. This is the test data taken from the laboratory experiment. By conducting a open circuit test, we got the generated voltage, that means line voltage, corresponding for the corresponding field current. Open circuit test, that means without a load we have excited the field current of an alternator from 0.1 to the rated values. By the way, we have generated the line voltage 180 to 495. To evaluate the regulations, we need the per phase voltage, that is converted from the VL. Since it is a star connected machine, that phase voltage is VL by root 3. By the way, we are getting 103.92 for 180 voltage. From this field current and the open circuit generated voltage, we created a OCC curve. That is, in y-axis we have taken the generated voltage per phase and the x-axis which reflects the field current. For the taken values, that means for IF with respect to the generated voltage, we made the open circuit characteristics. As like we have conducted a short circuit test also by applying the rated current, and we have taken the corresponding field current, we made the short circuit curve. Looks like this one. So since we are going to evaluate MMF method, we have to take the corresponding field current. That means for the first case, the V rated, V phase, which is nothing but 240, the corresponding voltage becomes, current becomes 0.63 for the 240 volt. So that we are going to take it as a IF1. That is nothing but IF1. That is a 0.63 nominally. Then, in coming to the short circuit current, rated current, the corresponding field current is 0.25. That we are going to take it as a 0.25 as a IF2. So as we know, that similar to the parallelogram forces, where the IF1 which reflects in the one axis and IF2 here. By making the resultant, it's similar to the parallelogram forces. That's why we can apply the parallelogram forces law. The resultant force is equal to root of IF1 square plus IF2 square plus 2IF1 IF2 cos of this 180 degree minus this angle, that is nothing but 90 plus that pi which is nothing but we are going to take any power factor, the pi angle from the power factor. This plus reflects the lagging power factor, this minus reflects the leading power factor. For the first case, we are going to solve for the lagging power factor. I have taken the three different power factors for cos pi is equal to 0.2 and cos pi is equal to 0.4, as like cos pi is equal to 0.6. As we know that IF1 which is 0.63 and IF2 0.25 and angle which is pi, by substituting 180 minus 90 plus this value, we are going to get that IFR, that is nothing but a resultant field current which is going to be generate the E0. So where 0.87, this is the IFR, resultant field current, we got from the MMF calculation. The corresponding voltage along with the OCC curve, which is nothing but 270. This is nothing but E0. This is nothing but E0. This is what we have to calculate to find the regulation. As we know the regulation formula, E naught minus VL by V into 100 will be the percentage of voltage regulation. So that E naught 270 we got from the graph corresponding to the field current of 0.87. That VL anyhow we know, that is the 240 voltage. From that we have calculated the voltage regulation of 12.5% for the power factor of 0. Similarly, we need to calculate for power factor of 0.4 as 11.6% regulation, and for 0.6 the regulation becomes 9.1 for the lagging power factor. The next case we have to evaluate for the leading power factor. That remaining parameter all are similar except as a wave sign signal here. As I told you, the same IF1, IF2. This is the predetermination method. So we have to keep some data as a predetermined, that is these data. Again we need to keep power factor as like 0.2, 0.4, 0.6 by substituting the of negative. We got the field current, resultant field current as 0.38. So then we E naught, that is nothing but the corresponding field current is 0.38, that corresponding voltage going to be 192 from the graph. This method we have to calculate this voltage got from the corresponding field current from the OCC. By substituting in that voltage regulations, we are getting the voltage regulation value in terms of negative 20%. As like we are getting some minus 17% for 0.4. So by the way, we are getting now different for leading factor as well as lagging power factor. So by keeping here, this is the unity power factor, this is 0.8, 0.6, 0.4, 0.2 and 0, as like here also 0.846. That means as like a power factor always reflects the unity, that value could be in between the 0 and 1 in case of a lagging as well as leading. This left hand indicates the leading power factor region, this is the lagging power factor region. From the data which we got by making the graph, that means first I'll let you explain. The value of voltage regulation is 12.5 for the power factor of 0.2. That comes here 0.2, that's come to around 12.5. As like when the power factor increases, that regulation drops. See, so that for the lagging, whenever the power factor increases, that voltage regulation drops and it comes to 0 at unity power factor. The next case, how to reflect for leading power factor, where also 0.2, that is in minus 20, that comes here in the negative peak value. Then 0.4, it again drops in the negative minus 17. So on it is coming like this. So it matches with the regulation curve of MMF method. So by the way, we can calculate the exact regulation of the alternator for different power factor. Actually speaking, that the topmost line which reflects the EMF method, right now what we done is the MMF method. What reflects from the curve means the MMF method which shows the higher regulations, that means which shows its take drops. Even though it's a predetermination, it's more drops. Is more, they're not exactly accurate, even close to the accurate. But that MMF which consider in terms of flux, so that results are closer to the accurate value. That's why we used to say that MMF is a optimization technique. This is going to be the pessimistic technique.